The following video explains the particle-in-a-box model in quantum chemistry and how to plot a 3D model on Python. The particle in a 3D box is a way of modelling the behaviour of a particle in a prohibited space. It can show the location of this particle as well as predicting the energy within this space. This can help to show where an electron lies around a nucleus, predicting the patterns of the particle. It can also give images of orbitals predicting the area in which an orbital is situated, as shown in the picture above. The model uses the Schrödinger equation to show the energy of the wave, the kinetic energy being in blue and the potential energy in red. It is assumed that within these parameters, the particle has zero potential energy, and beyond these parameters, there is an infinite amount. This means that this part of the equation is equal to zero when modelling the particle in the box. In a 3D box, there are three independent variables in the Schrödinger equation, so the equation becomes the following. The equation now has three elements. Wave function on its own is not significant. The wave function must be normalized to give it any physical qualities. This means the conjugated value is multiplied by the original value, showing the probability density. In this case, the conjugated value is just itself, as there is no imaginary values. In order to normalize the wave function, the integrated square modulus of the wave function will be equal to 1. This shows the maximum probability for a particle to be in a box. In order to do this indefinite integral, a normalization constant must be found to allow the probability density to be shown, showing the statistical properties of the system. In a three-dimensional box, there are three axes. This means that the normalization constant is cubed, and the three axes showing the value of the wave function will need to be added to one another, showing the probability density on all axes, giving the following equation. Here we have the wave function, the volume of the 3D box by multiplying each length value by one another, and the de Broglie wavelength of the wave on each axis of the wave. The probability density of the wave is equal to the modulus of the wave function squared, thus the wave function is squared in all dimensions of x, y, and z. First step was to import the packages in order to use certain commands within the system. The next step was to assign the limits of the legend of the 3D box. This was to be 10 to the minus 9 in both of the x and y directions. The quantum number was the next to be defined. In this case, an array was set up. The NP-linspace function set up an array showing numbers 1 to 3 in steps of 3. dtype equals int allowed the system to recognize the function as an integer and not as a float. Then there was a set of limits for the x values, showing values from 0 to L, or 10 to the minus 9, in steps of 360. After this, the value of the wave function was defined. Def was used to define a whole term here. The normalization value is used from a 2D plot and multiplied by itself to show the values in 3D. The terms are finalized by using the return function. This finalizes the equation and makes the statement final. At this point, the y array will be the same as the x, so this is defined here. xy equals np mesh grid is used to make a rectangular grid shown in the x and y axis. In order to incorporate the array into my 3D graph, the following for loop was created. This allows a set of statements to cooperate for this set of values in the n array. This line is used so that the following values can be assigned to psi_3D. This allows the actions described to be placed onto the figure plotted. Here the command allows a 3D projection to be shown, allowing the use of a z-axis. Here the x, y, and z values are being defined as well as the colour of the graph. The next three datasets show the labels for the x, y, and z axis. Finally, an event loop is made to display all the current figures and imports, allowing the commands to run, producing the following graphs. There are some similarities when plotting the probability of the wave function. However, the probability equation is used as a factor rather than the wave function. In this case, the probability density is defined as the square of the wave function using the same def tool. To allow the n array to function within this, the psi_sq is then defined to include all values of the array. Finally, I decided to change the colour to see its appearance to get the following graphs.